This question says, what is the percent ionization of a 5.3 times 10 to the minus 3 molar HCN solution? And then it gives us the Ka of HCN. So as we've done in the previous examples, we're going to start with the Ka expression. So the Ka expression for HCN is concentration of H3O plus, concentration of Cn minus, divided by concentration of HCN. And then we're going to use the ice table, the initial change in equilibrium. And if you haven't watched 2 questions ago, it's good to start with that because that's where we talk about the ice table the most. So this is the Ka expression. Now in the past, we've solved for pH, and in one case we were given the pH and we solved for the Ka. But in this case, we want the percent ionization. So the percent ionization is equal to the concentration of H3O plus, over the concentration of HCN, and because it's a percentage, we multiply by 100. So it's the percentage that breaks up from HCN and forms H3O plus, divided by the original concentration of HCN, times 100. I guess technically the equilibrium concentration, but in this case we're going to ignore X. So it's basically the initial and the equilibrium concentration are the same. So let's take a look at how to fill out this ice table. Well, we know the concentration of the HCN, which is 5.3 times 10 to the minus 3 molar. We know that initially we don't have any H3O plus or any Cn minus. We know that we're going to lose some amount of the HCN because it's going to form H3O plus and Cn minus, and we're going to gain some amount of H3O plus and Cn minus. We're going to go ahead and ignore this X, although we could check at the end that it's less than 5% or 10% of this, and we're going to get 5.3 times 10 to the minus 3 as the equilibrium concentration of HCN, because this X is going to be very small. Again, you could check it, and if it's not very small, you could use a quadratic equation. We're going to gain X amount of this, and we're going to gain X amount of this. Now we can plug into the Ka expression. So Ka is provided 4.9 times 10 to the minus 10 equals, this shouldn't be plus, it should just be X. X and X, so X times X, divided by the concentration of HCN, which is 5.3 times 10 to the minus 3. We cross multiply these two numbers and we multiply X times X, and we find that X squared is going to be equal to 2.6 times 10 to the minus 12. We then take the square root of this, take the square root of this, and we find that X is equal to 1.6 times 10 to the minus 6. You'll notice that this is 3 orders of magnitude smaller, so this is about 1,000th the size of this one, so it's certainly going to be less than 5% or 10%. So this is basically good. Now we can do the percent ionization. This is the concentration of H3O plus. Note that X is the concentration of H3O plus, which could be used to find the pH, but we're not asked for the pH here. We're asked for the percent ionization. So we plug in 1.6 times 10 to the minus 6 molar. And the concentration of HCN, again, we ignore the X, so we're just going to put in the initial concentration, which is 5.3 times 10 to the minus 3 molar. And we're going to then multiply by 100. And when we do that, we find that this is 0.030%. And I'm just realizing this is also proving that we can ignore X, right? Because this is 0.03% of this one. It's certainly less than 5 or 10%. So we can definitely ignore the X. So this is how you find the percent ionization, as opposed to finding the pH, which is very similar to 2 problems ago.